Look around you. The blades of a ceiling fan spin to give us a cool breeze. The wheels of a car rotate to move it forward. Even our own planet, Earth, is constantly rotating on its axis, giving us day and night. This type of motion, where an object turns around a fixed line called an axis, is known as rotational motion. It is a fundamental part of physics that describes a vast range of phenomena, from the smallest spinning subatomic particles to the grand spiral of galaxies. Imagine a single point on the edge of a spinning record. We can measure how far it has turned by an angle. This angle, denoted by the Greek letter theta, is called the angular displacement. A full circle, which is 360 degrees, is equal to 2 pi radians. This speed of rotation is called angular velocity, represented by the Greek letter omega. If an object rotates through an angle theta in a time interval t, its average angular velocity is omega equals theta divided by t. But what if the rotation is not steady? This change in rotational speed is described by angular acceleration, represented by the Greek letter alpha. If the angular velocity changes by an amount delta omega in a time interval delta t, then the angular acceleration is alpha equals delta omega divided by delta t. Its unit is radians per second squared. A positive angular acceleration implies that the object is spinning faster and faster, while a negative angular acceleration means it is slowing down. While we have introduced new terms for rotation, we should not forget the linear motion concepts we already know, such as speed and acceleration. These two worlds, linear and rotational, are deeply connected. Consider again that point on the edge of our spinning record. At any instant it has a linear speed, tangential speed Vv equals r omega. A point farther out travels a longer circle in the same time, so it moves faster. This is tangential acceleration, a sub t. A sub t equals r alpha, that's centripetal acceleration, a sub c. Its magnitude depends on speed and radius, a sub c equals v squared over r. There are parallel kinematic equations for rotation. Linear, v equals v naught plus at. Rotation, omega equals omega naught plus alpha t. Learn one set. Swap linear and angular variables. In linear motion, we have the concept of mass. Mass is a measure of inertia, resistance to changing motion. In rotation, the equivalent is the moment of inertia, I. It measures resistance to changing rotational motion. For a single particle, I equals sine mr squared. For many particles, I equals sine sigma m underscore ir underscore I squared. Farther mass contributes much more, r squared. Closer mass contributes much less. Solid disk or cylinder, mass m, radius r, about central axis. I equals 1 divided 2 mr squared. Hollow ring or hoop, same m and r, I equals sine mr squared. Notice the hoop has a larger moment of inertia because all its mass is at distance r, making it harder to spin. If you know I underscore cm about an axis through the center of mass, you can find I about any parallel axis a distance d away. The formula is I equals sine I underscore cm plus md squared. This is useful when an object doesn't rotate about its center, such as a door swinging on its hinges. In linear motion, a force causes an object to accelerate. The relationship is given by Newton's second law, F underscore net equals ma. This rotational equivalent of force is called torque, represented by the Greek letter tau. Torque is a turning or twisting action. When you use a wrench to tighten a bolt, you are applying a torque. The amount of torque you produce depends on 3 factors: the magnitude of the force you apply, F, the distance from the axis of rotation to the point where you apply the force, r, the angle at which you apply the force. The mathematical definition of torque is the cross product of the position vector r and the force vector F, written as tau equals r cross F. The magnitude of the torque is given by tau equals rf sine theta, where theta is the angle between the r and f vectors. This fundamental law of rotational dynamics is expressed as tau underscore net equals I alpha. Imagine a grinding wheel, which we can model as a solid disk with a mass of 5 kilograms and a radius of 0.1 meters. Suppose you apply a tangential force of 10 newtons to its rim to get it spinning. First, we calculate the moment of inertia, then the torque, and finally use tau equals y alpha to find alpha equals 40 radians per second squared. In linear motion, the concept of momentum P equals mv is incredibly important, especially in collisions, because of the law of conservation of momentum. Rotation has a direct analog to linear momentum, and it is called angular momentum, represented by the symbol L. For a rigid body rotating about a fixed axis, the angular momentum is simply the product of its moment of inertia and its angular velocity, L equals 1 omega. The law of conservation of angular momentum states that if the net external torque acting on a system is zero, then the total angular momentum of that system remains constant. If the net torque is zero, then L underscore initial equals L underscore final, which implies I underscore initial times omega underscore initial equals I underscore final times omega underscore final. A classic and beautiful illustration of this principle is a figure skater performing a spin. The skater starts the spin with their arms and legs extended wide. In this position, their mass is distributed far from the axis of rotation, which gives them a large moment of inertia. Then, as they pull their arms and legs in close to their body, they are decreasing the distance of their mass from the axis of rotation. This action dramatically decreases their moment of inertia. Because the moment of inertia has decreased, the angular velocity must increase proportionally to keep the product L equals 1 omega constant. This is why the skater spins much faster when they pull their arms in. The same principle explains why a diver can perform complex somersaults in the air by tucking into a ball, or why planets in elliptical orbits speed up when they get closer to the sun. An object in motion has energy by virtue of that motion, which we call kinetic energy. For an object moving in a straight line, this translational kinetic energy is given by k underscore trans equals 1/2 mv squared. A rotating object also possesses kinetic energy due to its spinning motion. This is called rotational kinetic energy, and its formula is k underscore rot equals 1/2 I omega squared. Many interesting situations in the real world involve objects that are both rotating and moving translationally at the same time. The total kinetic energy of a rolling object is therefore the sum of these two energies. K underscore total equals K underscore trans plus K underscore rot. A special and important case is rolling without slipping. This condition creates a direct link between the translational speed of the center and the angular speed of the rotation. V underscore Cm equals R omega. Consider a solid sphere. M equals sine 5 kilograms, R equals sine 0.2 meters, initially at rest at the top of a ramp. Use conservation of energy. Initial energy, mgh equals final kinetic energy. For a solid sphere, I underscore Cm equals sine 2/5 m r squared. And for rolling without slipping, omega equals sine V underscore Cm over R. Substituting and solving, we get V underscore Cm equals sine S cart, 42, 6.48 meters per second. Theory is essential, but physics is learned by solving problems. Let's apply the concepts to a couple of representative problems. Solving problems step by step builds mastery and confidence for exams. Keep practicing, and the world of rotation will open up to you.